Hello, we are Team Kayakity Quacks, and this is our concept presentation for a hoist to transfer athletes from a wheelchair to a kayak. We politely ask that at the end of this presentation you fill out a short survey with questions or concerns. Thank you.
One of the events that Disabled Sports Eastern Sierra does every season is kayaking. They go out to a number of lakes around the Mammoth area and always launch the kayaks from the lake shore since there aren't often boat ramps or docks available. This means that the surface where the athletes are transferred from their wheelchairs to the kayaks could be gravel, sand, pebbles, dirt, or any mixture of those. Also importantly to note is that DSES uses tandem sit-on-top kayaks where the athletes paddle in tandem with an instructor. DSES doesn't own their own kayaks and instead rents them every season from an outfitter. They always use ocean sit-on-top kayaks since they tend to be more stable and are also much easier to get into and out of. Some of the important dimensions of the Malibu Pro 2 tandem kayaks that DSES used last year are that they're 13 feet long and 33 inches wide at the widest part. The athletes also tend to sit in front of the kayak with the instructor sitting in the rear.
The current process for transferring the athletes onto the kayaks is a manual method. The athletes have to wheel close enough to the water, and since they're launching from a lake shore, that means they must wheel through grass, sand, and gravel. Once they are close enough to the kayak, they are transferred over manually with the help of 2 to 4 assistants. It is also important to note that the athletes range in size and abilities. They can be anywhere from a little kid that weighs 35 pounds up to an adult that weighs 250 pounds. Also, some will have complete upper mobility, while others will have limited or no upper strength, and some will have cognitive issues as well. Lastly, athletes take turns paddling. Some athletes will be out paddling, while others are simply enjoying a break on the shore. Now that you've heard the current process, you can imagine that it is very difficult to transfer athletes from a wheelchair to a kayak. Not only is it difficult, but dangerous as well. The athletes could be dropped during the process, or the assistants transferring the athletes could hurt their back in the process as well. We also recognize that we want to give as much independence as possible to the athletes. Simply because these athletes have a disability doesn't mean that they can't do what they enjoy whenever they'd like to. That is why we decided to design a hoist to safely transfer athletes from wheelchair to kayak on uneven terrain.
Although there are no existing products on the market that specifically meet our needs and requirements, we conducted background research on some similar products that transfer people from their wheelchairs to another surface. The first set of devices that we investigated were pool lifts. These work around water, which is very important for our application. However, most of the designs are meant to be anchored into the pool deck to provide stability, making them not very portable. There are also some designs that are advertised as portable, and while they have wheels and can be moved around on the pool deck, they all have large counterweights on the order of 800 pounds, again making them not very portable for our application. We also looked into hospital lifts. Most of these are much more portable and lightweight, but are designed to be used on a flat, even hospital floor. Also, given the intended use in a hospital, the independence of the person being lifted isn't really taken into consideration, as a nurse or hospital assistant would almost always be there to do the lifting. It is also important to note that all the lifting has to be done over the base supports of the device, limiting what kind of obstacles and locations these lifts can work around.
The kinesiology department at Cal Poly has their own adaptive kayaking program, which we were able to go to one weekend. A trailer, which was a previous senior project, is used. In the parking lot, the team will put the kayak on the trailer and strap it down. Then, using 3 to 4 people, the athlete is lifted manually and placed in the kayak. They then wheel the trailer down to the water and off the athlete goes. Key differences were that a boat launch ramp was used and all loading was done on the flat, hard parking lot ground. In one case, a Hoyer lift was used to get an athlete out of the kayak. First, a sling was laid down before he entered the kayak, so it was under him the whole time he was on the water. The Hoyer lift attached to the sling, and he was lifted out. A note to make is that the trailer allowed for the supports of the lift to go under the kayak. We will not have this luxury. Here are some of the requirements that were made by DSES. We know that house storage is an issue, so the minimal storage footprint is greatly stressed. We also know it takes about 4 people to transfer the athletes, and we want to cut this down to 1. The cost to design and manufacture will have to be less than the NSF grant that we were given. Here we have a list of our specifications. Our highest risk parameters are the weight and storage size. We have said that we are willing to increase the assembly time in order to meet the specifications for the storage footprint.
In order to find a truly creative solution to our problem, we participated in an ample amount of idea-generating activities. We started by a simple group brainstorming where we all met and sketched our individual ideas. This helped us see what type of ideas everyone else was thinking and allowed us all to get on the same page. Soon after, we decided to break up our design into its most important components. That is, the frame, power system, lifting mechanism, portability, stability, harness configuration, and the wheels and transport mechanism. We recognized that the frame will dictate all of the other components, so we bought some PVC pipes and started doing some frame mock-ups. This helped us recognize frames that could work and also helped us think of new frame ideas. In addition, having these mock-ups allowed us to think of ways to integrate all of the other components. Lastly, during the adapted paddling event we attended, we spoke to the athletes and caregivers to get their input on the feasibility of our solutions or any suggestions they had.
We decided the frame is the most important aspect and will dictate all other components. It will obviously need to disassemble into smaller pieces in order to be transportable, but safety is still our #1 concern. Our first design is called the Hoist. This design is based off the lifts seen in the hospitals. The athlete would sit next to the kayak and a pulley or hydraulic system will move them out of their wheelchair. Now, hospital lifts are able to have supports go under the bed to which the patient is being transferred. However, our product will not have this luxury, so the supports in this design will go over the kayak, allowing for the entire structure to not tip over during the transfer of the athlete. Some positives about this is it would allow the athlete to perform most duties in the transfer, but the cons are that it's bulky and difficult to move. The kayak and athlete move to hoist instead of moving the hoist to the athlete and the kayak, and the supports would interfere with the launching of the kayak.
Another concept design is the chair. The chair is basically a specialized wheelchair that interfaces with the kayak, with the ultimate goal being more independence for the athletes. The idea behind the chair is that the athletes could wheel themselves across the beach easily and independently, and then wheel right over the kayak. A mechanism within the chair would then allow them to lower themselves directly into the kayak. However, this concept still requires a transfer from the regular chairs to the transfer chair, and given the increased width to be able to fit around a kayak, it might be too wide for the athletes to comfortably wheel.
The trail lifter would allow ease of transport for the athlete as well as the kayak. The kayak will be loaded onto the trailer in a parking lot or a loading zone, and the athlete will then be hoisted into the kayak from a lift that is attached to the trailer. Once in the kayak, another volunteer will push the trailer into the water and launch the kayak onto the lake. Some positives about this one is it would be easy to transfer the athlete as well as the kayak across any terrain. However, the company would prefer to not have to take the kayak out of the water every single time to switch athletes.
The mover is a simple four-legged structure that will go over the athlete in a wheelchair and through some sort of lifting mechanism, lift the athlete off their wheelchair. Then, with the help of an assistant, the whole structure will be pushed over the kayak and the athlete will then be able to lower themselves down. This structure is very portable, easy to operate, but also very stable thanks to its simple structure. The dog slide idea came from the thought of the athlete literally going down a slide to their seat in the kayak. In this design, the athlete would wheel up a ramp, move into a sling, and then mechanically be lowered to their seat. Key features to this would be that the kayak could have a possible docking station and go under the ramp, making the distance traveled by the athlete lower. However, to follow the Americans Disabilities Act, the ramp would have to be over 12 feet long. This would make the storage footprint very large.
The side dock is an A-frame type structure that has a sliding hoist mechanism along the top. The kayak would be stationed on one side of the structure, and the athlete would wheel up alongside it. They could then be strapped into a sling and lifted from their chairs before being moved by some sort of crank mechanism to the side over the kayak. In order to accommodate both the kayak and the wheelchair, though, the side dock would have to be very wide, making it harder to achieve a small storage footprint. In addition, since the athlete would not wheel right up to the water's edge, the kayak would be farther up on the beach, making it harder to launch.
Our next design is called the swiveler. In this design, the athlete will be lifted in the air from an overhead hang. A crank will be placed on the main base, allowing the athlete to operate it themselves. The crank will cause the entire structure to turn on a pivot point, and after turning 180 degrees, the athlete will be placed directly above the kayak and capable of lowering themselves down. Now, some positives about this one is it allows for independent use by the athlete and close to the water access. However, to make it around the back edge of the kayak, the structure will have to be very large. Also, it would be difficult to turn in rough terrain.
We compared the three best and most plausible frame ideas in a decision matrix. According to our study, we found that the mover was the best option. The trail lifter simply did not meet the needs of DSES, and as for the swiveler, we felt that it would just have to be too large and may be difficult to use in a rough terrain.
One of the subsystems we looked into was the wheels, or how the device is going to be transported over the rough terrain, which could range from grass to dirt or mud, sand or gravel. Some existing all-terrain wheels include the basic mountain bike type tires, really wide wheels for use on sand, and even big tank type tracks for a variety of surfaces. We decided that for our applications, the tracks would not be as portable, and given their complexity over the other designs, they would also be more expensive and there would be more maintenance needs. So given our range of surfaces including sand, we decided it would be best to combine several attributes and have wide wheels for going over sand with some simple treads on them to provide traction on other surfaces. Another important subsystem that we looked into was the sling, or how the person is actually going to interface with the device. There are three main types of slings available on the market. One of the most commonly used ones is the U-sling. These come in a wide range of support levels, including some that have full back support and headrests, and others with just a support across the mid-back. They're fairly easy to get into and out of while sitting, since the straps wrap under a person's legs and the butt doesn't have to be lifted. Hygiene slings are a subset of U-slings. They're mainly used for patients' bathroom use, since they're very easy to get into and out of, and also make it easy to get the clothes on and off. Finally, full-body slings provide the most support and are often used for amputees and others that need the extra support. However, they are much more cumbersome to get into and out of, particularly in a sitting position. This is because the sling actually goes under the person's butt, so they have to be lifted or repositioned somehow just to get the sling in place.
We constructed a decision matrix to decide on what type of sling to use for our hoist. We chose to compare a full body sling, which is very secure. However, the athlete would need to be completely lifted in order to get the sling under his bottom. Our team tried to create mock-up designs of a different type of sling that would safely secure the athlete but prevent having to lift them in the first place. We created a rigid body frame or a rigid frame sling with L-shaped bars that would have two main pieces of fabric. The first would go behind the back of the athlete with the rigid bars on both sides. The athlete would then take the second strip of fabric and slide it under his or her legs and attach it to the rigid frame. Then, cables to lift the athlete would be attached to the rigid bars and would lift the athlete like they are sitting in a chair. This design worked and was easier than the full body sling, but had added unnecessary weight. Also, it may not have worked for athletes with above-knee amputations. We then created a U-sling. This sling slides down the back, then wraps under the thighs of the athlete. Cables to the pulley will attach to connection points on the back and between the legs. This type of model sling is widely used and is the best possible solution for the kayak hoist. we looked into 3 different hoist mechanisms that could work with our design. The first one is a differential pulley or chain hoist. Some advantages are that it's self-locking and it also offers excellent mechanical advantage. However, due to this mechanical advantage, we would need a long chain pull for short weight displacement. We also investigated a multi-pulley system. However, we recognized that we would need a lot of pulleys to get a reasonable mechanical advantage. That would mean that our system would be harder to maintain, harder to set up, and would also add unnecessary weight. Lastly, we looked into hydraulic pumps, commonly used in hospital lifts and Hoyer lifts. Some advantages are that it's self-locking and allows gradual lift and descent. We constructed a hoist decision matrix to decide upon the chain hoist pulley system or hydraulic lift. The chain hoist was our winning mechanism, and what really set it apart was the great mechanical advantage it provided to the user. The higher the mechanical advantage, the more independence our athlete will have. We will now show you a short video we found on the internet demonstrating the capabilities of a chain hoist.
Hey, I'm Ryan Bavetta, and this is a chain hoist, and this is 150 pounds of popcorn kernels. Yet I can lift it by gently tugging on this chain. Pretty sweet.
Now that we have decided on all of our components, here is our final concept idea. The image shows how our structure will be collapsible. Also, we decided to allow the structure to turn and created a swivel in the back 2 legs. The wheels will be locked and the frame is what will cause the turning. This design created a few critical points which will be reviewed and analyzed further. Another option is to keep the entire frame rigid and allow the wheels only to turn as we had in our initial concept. The image also doesn't show the chain hoist, which will be placed directly below the intersection of the beams on top of the frame.
In order to make appropriate engineering analysis, a material had to be selected for the structure. The main criteria were that it needed to be lightweight, strong, corrosion resistant, but also all at low cost. We found that aluminum alloy 6061 would be an appropriate material selection. It is strong, but it is also relatively lightweight and cheap. Aluminum is corrosion resistant, therefore will not rust and can go in and out of the water. For safety concerns, we needed to find the minimum width of beam that will be able to support our maximum load. With square beams chosen and a thickness of 0.125 inches, we found that to prevent failure and bending stress in the columns, a minimum width of 0.749 inches was needed and 0.564 inches to prevent buckling. So we chose 2 inches in our model and then used this to find the factor of safety in the cross beams. The shearing factor of safety is 12.4 and the bending factor of safety is 6.23. The critical points can be seen in the figure, but with our dimensions there should be no failure.